right screen. Okay, hopefully. So we'll start by just looking at some of the equations. So again, this is great extension to the previous time when we looked at and implemented some of the principal component analysis for dimension reduction. In this case, we can again apply the same type of math for this problem. So, and again, this is really interesting, I think. So the process of how it actually works is based on some graph theory. So one is that like in the description of the spectral clustering, as far as I have found, they say that there should be a unidirectional graph, and so that would mean that there should not be actually loops, but in general, all of the implementations that I've found, and like they don't care about that. But here there is something called minimal spanning tree. Minimal spanning tree. So this is this can be used as the adjacency matrix, or you can construct matrix of connections between all of the samples nodes, basically based on the closest node. And of course, if you do this, like let's say in some recursive manner, you can try to eliminate and just make a graph that contains the least distance between each of the nodes. And this is something that some more advanced clustering methods like HD, like just what was the name? HD scan, I think it's called HD scan, and HDB scan, and optics scan, and optics. So they use really clever method of having the density function. So you can already see that in this graph, like if they are basically points. So what is unidirectional graph? So that means that you have just one in. Well, so the edges between the nodes should be pointed in one direction. So in this case, all of the edges are pointed towards kind of the center, and they are not having, there's also there should not be loops in my opinion, but anyways, so for the HDB scan and optics, the minimal spanning tree is required, but for the spectral clustering, as I found out from the implementations, and I guess the theory should confirm it, is that this is not always required. So just I wanted to say that a few words about these clustering methods that we could look next time. They're a really clever way to calculate step by step the sum of the edges, and in that way you can kind of estimate the density of each of those clusters. So they would calculate based on those edges how, like kind of, you could think of what's the average distance between those nodes in specific area. And as you see, they can like cluster also shapes that are not based around the mean or median. So that's great. We will look at that hopefully next time, I think. So that's one thing, but the minimal spanning tree as itself, you can use the matrix for that description also for today's session, but I didn't have time to find some. So there is a Prim's algorithm that calculates this stuff, but if somebody knows in Numpy how to get the adjacency matrix from minimal spanning tree really quickly, you can share, then we can try out that one as well. So here there is another of this from just from Wikipedia. So the graph, and then we have the adjacency matrix. So that is what I mean by that unidirectional. is that you will have the just between each of those so so let's say the width and height, or the rows and columns, represent the nodes here, A, B, C, D, E, F, G. Here, if you can think like, maybe you can, maybe for those of you seeing this first time, maybe you should add something. So there's, let's say, A node, then there could be, except the Google Jamboard is a little bit slow today. So the B node, for example, there would be, and then C and so on, right? Many nodes. And the same can be then represented in these matrices. So there will be like A, B, C in columns, and then in rows A, B, C, B, C. And except, of course, I should have something in between here. So like something like that, I guess. Anyways, hopefully you get the point. So then the 1 means that this is connected, and 0 means this is not connected. And the degree, if you see, it's also interesting that that's on the trace line. So that would say that, for example, how many other nodes there are connected, or maybe that could be also like some. Also, it could be with regards to the weights or some distances or something. Then what you do is you can get also this form. This is Laplacian graph matrix. This form is also really nice for describing all of these kind of connections and weights. And also in the implementations that I've seen, they kind of even don't bother of constructing them step by step. So let me quite quickly find something. Okay, anyways, I don't want to waste time here. So let's add just here some. So this is D. This will be A matrix. And the other one will be L. So A and L, and probably you can see already that you can get the L matrix by subtracting D from A. Where is this one? So this is D matrix is, not D, but L matrix is D minus A. So you can do that. Okay, fine. So the most interesting part is that kind of Laplacian matrix. Basically, you can calculate that either like step by step, if you have the adjacency matrix and the degree matrix, or there is another ways that we will also quickly check that on the CPy implementation, and then also can do ourselves. The other ways are just calculating the pairwise distances with some kernel function, very similar actually to what we did with PCA. And just looking for the correct equation now. Maybe I should just look from the code then. Okay, so the fun thing is that from this matrix, Laplacian matrix, if we would calculate eigenvectors and eigenvalues, as we did last time for the PCA, and the PCA, the eigenvectors and eigenvalues represented, so the eigenvalues represented kind of the variance over some axis, and or like over some transformation linear, and the vectors itself then represented those axes of those hyperplanes in those linear transformations on which we can project. And then we wanted to use those axes where we have the highest variance, if you remember that, hopefully. So, and then here we can do the similar approach. I guess the better would be just to then write it down. But maybe I should just remind you about the eigenvalues and eigenvectors. Just a second. We'll find my LaTeX. LaTeX it. Okay, so let me share the full screen as well. Okay, like that. This will be fine, hopefully. So there is last time we looked at the eigenvector and eigenvalue equation, and we also looked how to then calculate the first the eigenvalues and then the vectors using discriminant, and that whole operation is actually implemented in Numpy. And but there is it's actually called spectral clustering because it's coming from that part, and there is something called the spectral theorem, and it looks something like this. So what is this? There is some kind of problem here. Okay, so lambda, just a second, and ut transposed one. No worries, we can implement that very soon. So okay, actually maybe you should use the, was it a lot small or big one? Because last time I think I used small one. Yeah, like that. So yeah, so basically there's some kind of transformation. So this is the spectral theorem, and basically that means that there is some kind of transformation that you can have like with the dot products of the of those lambda vectors, and then transposed one, and you would get back the same this transformation. And that part is easy to check, and that works. But then you can also, I think it was like multiply both sides with the u, if I remember correctly. So just a second. Sorry, I'm a little bit slow. So if I multiply both sides with the u, and then this part would then become as an identity, right? So then the ut transpose dot product with u should be, I guess, identity function. And by the way, maybe we should call this not u but v as it was before. Sorry for that. So v, that will be the eigenvectors, and the lambdas will be the eigenvalues, right? And then we can reduce that part on the right side, and we get back the equation that we used last time. So, and for that equation, we have the Numpy linear solver, so we don't need to calculate and actually write the whole long line of equations for just solving with determinants those lambdas, and then when you have the lambdas, you can solve the vectors as well. Anyways, I think it will be much better when we start implementing it. So this part, and also maybe just visually to remind you, I should quickly find the previous time when we used that part of the code. So Jamboard, I think there was one nice picture that I included in the okay, my Jamboard is not working. Okay, so okay, this one, Jamboard. Sorry for, okay, PCA, found it. So the Jamboard from previous time, we looked at depth of solving those equations, and I think just there was one visual that kind of helped to understand that transformation. Of course, those of you who know this by heart, so there's no problem. But basically, these eigenvalues and vectors would represent those kind of these transformations for data points. So there's a lot of blue small data points, and these are very specific ones because they are kind of orthogonal, or like they're matching the axis, but they could also not match the axis. And here these kind of the eigenvectors would be calculated along the axis with the most variance, kind of actually to just cover all of the kind of variances that we have in the data set. But with these, you can select those ones that are the longest ones. Here, the lambda is 5, the longest one. And here again, the lambda is 5, the longest one. And then we would project on that axis where we can preserve the most variance. If we would project on the green axis, we would have a lot of overlapping points and we would lose the variance. And that's not optimal for reducing dimensions. But also the fun thing is that for the spectral clustering here, if we feed in the not those kernel trick functions, but if we feed in this matrix of the Laplacian graph matrix, or the kind of adjacency matrix with some kernel function, then we get some very interesting properties that are covered actually inside that spectral clustering. And those properties are, I think, basically two. So one is that there is one, so okay, let me check. So first, after calculating the V and lambda, the eigenvalues and eigenvector and eigenvalues, the eigenvalues are lambda, vector is V. So when you calculate those, you can order by eigenvalues. So order, so let's add step by step. So first you need the adjacency, well, so how it's spelled, adjacency. Okay, so first you need an adjacency matrix, then the Laplacian graph matrix, or you can use also some this kernel function for this adjacency matrix. For example, the radial basis function, exactly the same way as we did for the PCA. So that's the first thing you need. Then, of course, again, the same way as we did before, we calculate the eigen values and eigenvectors. So they represent kind of this linear transformation that represents the distortion of the data set, basically. Or in this case, again, kind of would say, kind of not real, well, yeah, something like a distortion. So now the next interesting thing is that you can order ascending by the eigenvalues. By the way, if at some point I say something that is not correct or something, you can correct me on the chat if you know better, because I'm a little bit more specialized in some other areas, but these things are kind of important as well. So usually I use pre-made stuff, and I will show you just in a second about the pre-made stuff as well, but it's kind of important to understand also the parameters for that pre-made functions. So order ascending by the eigenvalues, then there is if statement, basically if k, so the k is again the very important number for the clustering. There are some algorithms, as in the first slide I mentioned, that could work without the k. So there are also some others like g-means, x-means. The g-means is based on the Gaussian distribution. And then there is also x-means and others with some heuristics. So the k is the number of clusters. That's why we also have the k-means. And today we'll do a quick k-means as well, because you'll see. So if the k is 2, so that is one specific case where this works really nicely. So then you can use something called Fiedler number. I have not really researched, unfortunately, Fiedler vector, like the historical basis how it all happened. I think it was related actually with the physics, and there was some other name of all of this stuff. Just let me check in a sec. Maybe I can find what was the name of those matrices. So the Laplacian graph matrix, I think it was the Krichkov matrix as well. And the Krichkov was physicist, I think. He was working with waves, and there is a connection with the wave equations, and that's why it kind of works. And it kind of represents the idea of that if you have just the two clusters, then there would be some kind of eigenvector that would describe kind of the middle point for the wave, where the wave is above this vector and below this vector. And then this really nice kind of representation of the waves, where it's like plus or minus, and it separates perfectly these data points just in two clusters. So that one is specific point. So this one will be the Fiedler vector would be in the V vector, the second vector in the list, basically. The first one, we'll try to plot in a second. I think the first vector had the lambda of 0, and the second one is then the first that is actually separating the space. So that's kind of interesting. So first one, I think the second one, basically second one, where lambda is higher than 0, and here then we can use this Fiedler vector. Maybe I'm probably pronouncing it completely wrong. So here we can use then this one where it's like above 0, then this is a cluster 1. If it's below 0, then it's cluster 2, for example. So this is like your condition for clustering. So condition for clustering. Okay, so that's one. Then the other thing is then if there is more than 2 clusters, so if K is above 2 clusters, then you would cluster together the eigenvectors itself, or I think it could work also with the clustering of eigenvalues. Really not sure which one is better at this point. Should research a little bit more theory. So then there is like k-means. So the very simple k-means, or k was called medians, or some kind of very simple clustering method. By the way, I also saw that there are some really cool clustering methods recently published, very simple ones as an alternatives to these ones. I think it's one that was published recently is cluster RQR, cluster QR. I think it was 2017, and they show in their results kind of really nice clustering. Wait, maybe I can share this one. Hopefully it works. But we'll do this in just in a second together with that template that I shared. So this is from GitHub. These guys who published the cluster QR algorithm that I have not yet examined in detail. They show that, okay, this is not what I wanted. So they show that for example, for feeding images, of course you can, this was something that the computer scientists did some long time ago, before having the segmentation models of deep learning and stuff. They just feed in the image, and each image pixel have, of course, RGB channels, and that can be interpreted as a vector. Then you can just cluster those channels, and so those pixels. And here you can see like on the bottom side, there is this new algorithm that they published, cluster QR. Seems really nice working together with the spectral clustering. But with the spectral clustering, normally like the simplest one would be to use k-means. That is not perfect, but still works. So, and then you would cluster not the data points itself with the k-means, but you would cluster the v vectors that are basically, you could cut them, at least in some implementations. I saw that you could cut them just by the k dimensions, but basically you can either v or lambda. So both could work probably. I tried with the eigenvectors, and they worked in some cases. We'll see that in a second. So and then when you have the assignments of the labels, then the next step is easy. Probably it would be better to code this stuff, and then maybe it would be easier to understand. If you have some questions, you can write in the chat. Probably you have, and like I'm not really that big an expert of the explanation of why it actually works, but it's related to the physics and the wave equations. So, but we can code it and check it, and that's important for the thing of deep metric learning, because in deep metric learning we want to have some kind of assignment of these embedding vectors. So the embedding vectors, for example, we train on one set of data set of some faces. Let's say we have 1,000 faces, and then we have some production set of faces that are not included in the training data set. And because they were not included in the training data set, they do not cluster very nicely, but they do cluster. So in general, they kind of like overlap a bit and stuff like that. They might look something like this actually. So if I run the code here, if you could imagine that those blobs are actually some 3 faces, and there are actually 3 clusters, but they are not perfectly separated. And then these spectral clustering methods, like kind of are one of the go-to methods that usually you see in the papers. They use PCA whitening plus spectral clustering. That's one common pair. We looked at PCA whitening before, and now we're trying to look at the spectral clustering. So we'll start from the top and then go down. So I mean, we'll start looking at the simplest version, where we can just use the sklearn implemented version and then try to replicate that our own. I don't guarantee that we will completely succeed, but we will succeed at least in some capacity. So again, I say that hopefully it's not take too long. So the way how you should do that in your own like deep metric research would be probably to use a pre-made function, but at the same time with the awareness of the parameters that you will see just in a second. So let's say there will be the clustering algorithm that will be spectral clustering, of course. And here we have a ton of parameters, and these parameters start making sense only probably when you implement it by hand. Otherwise, they look like kind of not that important, but they are. So one is the n clusters. So that's something that we should know for this method. As I said in the slide, the first algorithms were really powerful that use some other methods. Where you can estimate the number of clusters using other heuristics. So here there is this is K3, so the number of clusters. Maybe I should add it here. So K is usually this name for the clusters. That's why there is the algorithms called G means, K means, X means, all sorts of those. So then the affinity matrix, again, the first thing that we already know from what I explained before, that is that matrix that would determine the kind of neighborhood of the graph nodes. And by default, that is radial basis function, RBF, but it could be also something else. The radial basis function we implemented last time, and we could do that just in a second if you want. But okay, let's leave it as it is right now. Just estimate some baseline. So that's fine. And for radial basis function, of course, there is a super important parameter gamma. By default, this one is set here as 1. And then there is also very fun, if you look, there is a k-means, the assign labels function. Actually, should I go here and check what options do they give? The assign labels discretize, that's another way of clustering, less sensitive to the random initialization. Okay, yeah, so there is another point that I forgot to mention. Maybe these implementations almost never use the minimal spanning tree for the affinity matrix. Is that that would be very sensitive to the noise, because if there is a noise, then probably that graph would look a lot noisier. So they would not be clean, as nice tree as that as you saw. So okay, let's keep this short. So okay, there will be y prim. So the y is actually real assignments. Let's use y prim as our predicted assignments, or what's the clustered assignments. So here, fit predict and over y. So I think it should work. Or x, let's see. Hopefully it works. And if it works, I will drop that on the Jamboard as well. Okay, I think it works. It's actually almost the same as it was in the reality. Of course, we cannot predict those complete overlaps, but okay, there's another point to that. So here we have just 2 dimensions, but of course the embeddings have more dimensions. Embeddings might have like 128 dimensions, then we PCA whiten them to 32 dimensions, and then basically if we do the PCA whitening with it's like if we redo every time we can do the nonlinear version with radial basis function, then we can separate actually out these middle parts. So if we do the radial basis function, it's actually possible to separate out those overlapping things sometimes. So that works. I will add this to the Jamboard. So just a small example, and then we'll try to replicate the same thing with step-by-step code. And let's see how then it works. Okay. I also show the moons. So if you would run this with the k-means clustering, it would also work, of course, because there is some kind of mean vector around each of those clusters. But if we would try to do that for the moons, it would not work, definitely. But for the spectral clustering, it amazingly works. And also it works for that minimal spanning tree algorithms that I was actually, when I started doing this, I was hoping that we could do minimal spanning tree, but then I discovered that that is not optimal for spectral clustering actually. So here, this didn't work as I expected because there's actually 2 moons, not 3 moons. So if I run it again, still not great. So the minimal spanning tree clustering algorithms would be able to handle this, but spectral clustering also should be. Let's see what we can do here. So there is a k-means, clusters, gamma. Maybe we can play with gamma of the radial basis function. The radial basis function, if you don't remember, looks like this. So exponent of minus gamma multiplied by the distance between some x dimension xi minus, so basically not xi, but between each of the points. So xj or something. This could be just squared Euclidean or cosine or something else. So something like this, and that definitely affects these regions. Maybe if we try lower gamma, hopefully it works. Nope. So let me think what happens if I try to run lower gamma or higher gamma. Do you have some ideas how to change parameters? That would be also great. If it will not work, then we will just implement our own version. So just a second, exponent of 0, that's 1, right? So, and if I try to do something and that is closer, that will be make it everything closer. Gamma doesn't work. Sure, maybe this is not a good metric. We'll try something else as well. Okay, it works with gamma 10. It works. So if you just try some experiments, like if you know that exponent of 0 is 1, and then everything below, everything not below, but everything like 0 point something, this is everything close to 1, and then we start increasing it, then it exponentially increases. That is basically what it means, is that here in those half moons, in the sections where they are close, both moon parts, if we add gamma larger, then we kind of amplify that difference there. So that's why it works. So great, but we could not do this ever with the k-means, but it could work. It definitely works with minimal spanning tree algorithms that I really like. And I was really disappointed that for the spectral clustering, they are not optimal. So anyway, so this is for one part of the code. Maybe I should also drop this to Jamboard, and then we'll do the manual part of the code. So yeah, sometimes to run these functions, it's great to either plot them. So the plotting is the best thing. Then the second best thing is guessing them a little bit, to like calculator and stuff. So anyway, let's do the other part of the code. So okay, let's see. So I will comment down this one. Well, not like that. Well, okay, let's try to replicate the same behavior with our own code. Okay, so let's do the radial basis as in this case as well. So the kernel function. So one is that we could do that minimal spanning tree. Maybe if I have time, I can like show that next time. But oh, sorry, what I'm doing, this is completely wrong. So this will be the affinity matrix here, and the gamma, let's say, will be then the 10 as before. So this will be the exponent of gamma, and then we can use the pairwise distances. I think it should be fine with the x and metric Euclidean, but it could be something else as well. Euclidean, right? Hopefully that works. Then I think we should do the part of the converting to the Laplacian matrix, but I actually am not totally sure that we should do it. Maybe at least in some implementations I saw that you can skip that part, but like theoretically I think that should be included. So then there would be the flattening of the diagonal function needs the flattened version. Numpy flat. Okay, there's not the flatten. There were 3 types of Numpy functions to flatten stuff. So one is flatten, one is reshape, another one is ravel. But why can't I get the flatten here? Well, I think it should be, I guess it's at the end of the matrix then. So np sum of the a axis 1, so that would be the axis 1 would be then for each of them the sum of distances, and then the flatten, right? We got, and then we can calculate the L, that would be D minus A. Okay, so and then the part what was previous time, lambda and B. I'm not writing lambda because lambda is keyword in Python. So lin alg eigenvectors and values. So it's an eigensolver. Basically, the eigensolver, really simple stuff, but really, like at the same time, not nice to calculate because if you look at the previous session's video, you saw that there was like this matrix where we need to calculate the determinant, and when they calculate the determinant, the lambda appears in multiple places in the matrix, and then it becomes either quadratic equation or cube equation, or like really not nice thing to solve. So that's why it's great that there is a solver for that. So then the indexes will be sorted by the lambdas. And if you remember, for the PCA projection, we would just take the biggest lambda and would project on that one. That would be then really nice way to reduce dimensionality. But here, at least from the understanding that I have seen so far, we should take what was the name of that one? The Fiedler vector, that is the first one after the zero lambda. Actually, probably would be nice to plot it. So plot lambdas. Let's see what we have there. Plot show. And we could maybe exit here just to see what the lambdas look like. So I have seen some really nice graphs where the lambdas like kind of jump. So here there is the first one is 0, then the second one is really something very small, and then it starts growing. Okay, this one looks like that. Let's check how it looks like with blobs. So 3 clusters, maybe I will reduce the standard deviation, so it's a little bit cleaner, just to illustrate the idea. So the lambdas, okay, whoa, now they look really interesting. Was not expecting this actually. So the clusters, standard deviation 1, 3 centers, and it starts by, not by lambda 0. Let me check. Maybe we should try to use A directly. Let's check with this one. As if that would be affinity matrix. No, it doesn't matter. Okay, that was a little bit unexpected. I thought it should be something else. Let me check. Maybe I have some mistake. D minus A, should it be like that? Yes, it should be like that. Euclidean gammas. What would be if I try to not use the radial basis? So just the simple Euclidean distances as that kernel function. Okay, now the first one is 0, and then there's a jump, and then there is slight reduction, then there is a noise there. So, but it's still not looking that great. So I have seen nicer lambdas distributions. Let's see. Okay, still not great, but at least there is some kind of. So if you can think of that, you could cluster these together in, let's say, if you have 3 centers here. So probably the first ones are on the peak side, then there's middle part, and then there's third part. Hopefully that would then separate that those blobs quite nicely, but we'll see. So, okay, let's keep writing this. So then there will be K. So the K, as in previous time, we defined that one. I think in the first time, let's start with K2. So, and also reduce the centers to the 2 centers of the blobs, how it looks like with the 2 centers. With 2 centers, actually doesn't change that much, but still. So anyway, K2. So if K is basically 2 or smaller, or basically smaller than 3, then in that case, we want to use that Fiedler vector. So we can maybe just write it Fiedler. Not sure why it's probably physicist or so. Here there is. We can take the V vectors and then select from all of the samples that we have. So if you have 1,000 samples, we would have 1,000 by 1,000 matrix where there is the connection between all of those nodes, or in this case, the weighted connection is the distances. And here we could then select not the 0 dimension. Actually, I'm also not sure about this one because I selected actually lambda. Oh no, that's fine. The lambdas is then the first one, 0, and then the second one would be that one that we need, hopefully. So we can use that one, Fiedler here. And then let's say Y prime would be using just where it's above 0 or below 0. So that one we could use, let me think. So there will be light labels. That will be the first dimension. So we could probably write it down in multiple ways. Let's try to write it in this one. So if it's above 0, then we could multiply this by 1, and then it should be 1 or 0, hopefully. Let me check if I add the breakpoint here, if that shape is what I want. So that would be like a sine, I mean like wave function, where there is like above 0 or below 0. And that is kind of like the way how data fluctuate. Let me check what is this. Yeah, okay, this is fine. This is fine. So this will work, hopefully. So if I uncomment these and try to run it with just K2 for 2 blobs, hopefully it will separate them well. Yes, it separates them well. So that's beautiful. So the first one works, and then maybe we can try also with the radial basis function. Just double check that everything is right. Okay, the radial basis function is not great. The gamma reduces so the gamma mixes up everything. So if I try to do very small gamma, let's see. Okay, now it works. So that is really key thing actually to remember, that the PCA, this kind of the dimension reduction algorithm is not always like linear version. You can choose. There are many kinds of PCAs, and some of them that are not non-linear usually use the radial basis function, and there is a parameter gamma. I think it was divided by the dimensions, like I mean the samples divided by dimensions or some kind of that default value, but that is not always the optimal value. And yeah, in general, you could not rely on default parameters if you use something that is non-linear. So here in this case, really nice example. So anyway, let's keep going then with the 3 centers. So if I add the 3 centers, I will also post this in the Jamboard just in a second if everything works. So with the 3 centers, but then still leave the K2, it should split them in 2 parts. Let's see. So split actually really nicely. So there are 3 clusters, but it looks believable. So so the K2 works. So then let's move to the K3. So that's a little bit more difficult. So here, else, then we should cluster these k vectors. So then the vk's, so there will be the eigenvectors defined by k's. So this is something that should be experimented as well. I'm not totally sold about the way how I have seen the implementations. In some implementations, I saw that you would select from the Fiedler vector up till some k vectors, and then use those to cluster together as the basis for labels. But I believe that you could also cluster just everything after the first dimension. So we'll see. I will try first with this approach. So then the next part is k-means clustering, right? So one quick way how to do this is using the again sklearn, but we will do also this by hand just in a second. So today I just want to do from top down. So give some existing functions and then decompose them. So here y prim would be VQ, that comes from, if you look, VQ comes from CPy cluster vector quantization or something. So then there is a k-means 2. I think it's kind of optimized. Something is cooler than k-means. So anyway, so you can use k-means and then vk, and then we should cluster this by k clusters. So where's the clusters? K, yeah, k clusters, right, like that. Let's see how this works. So with the three blobs. Okay, this doesn't work that well. So let's see if I add here the k. Okay, now it works a little bit better, but still not great. K plus 1. I don't like actually this kind of approach. Okay, so let's try also clustering the lambdas probably. So let's see what we could do with lambdas. So the lambdas then are the zeros from that part. Let me check. I just want a little bit experiment. I will return to regular program just in a second. Just don't like the result actually. So, but that is well, maybe it's not working because I'm using the radial basis function. So if I move back to the simple Euclidean, maybe it would work. Nope. And if I increase the dimensions here, okay, increasing dimensions definitely doesn't help. So okay, let's check again with simple Euclideans, just the k2. Okay, that works. K3, then with this one will be fine. So just a second. EQ. So okay, I want to try the lambdas as well, but I don't like that the first one will be 0. But let's see. Lambdas. Can we cluster just the scalar values, scalar vectors? I hope we can. Okay, the lambdas didn't work that well. Yeah, so these should be clustered by the vectors. Not sure. I think the k-mean should work, but still, they kind of don't want to work. Oh, okay. The iterations, only 10 iterations. Maybe that's the problem. We have 1,000 data points. Okay, that's again good point. Why it would be great to implement these algorithms by hand, just to understand better how they work. So the iterations if there is just 10 iterations, that should never work. Okay, still. Maybe they are too close, those two things. So let's try to reduce the standard deviation of the cluster. Still strange. Okay, I'll try just by hacking another idea. Okay, with this works. Okay, I think that the operation of calculating Laplacian matrix for the graph is necessary only if it's not weighted already. So, but in some cases it might work, but I'm not sure actually, but I think it works. So if we had the adjacency matrix where it would list the zeros and ones where it's connected, then we would have the degree matrix, then probably that would constitute the same as if the pairwise distances with the kernel function. Not really totally sure about that part, but it seems like that it works with this kind of code really nicely. So if I try with K2, with the two clusters, and then we'll try with the moons as well, just in a second. And then, okay, this works as well. And okay, so, okay, let's see. These will be 3, and then let's move up back the moons. So the 2 moons with the Euclidean distances. Okay, that Euclidean is not great with 10 gamma, a radial basis function. Great, it works. We replicated the implementation with the. So my mistake was to add the Laplacian algorithms. I mean the equations here. So I guess I don't know the mathematical proof at the moment, but there I guess the kernel function itself gives already the matrix that we need. So anyways, we could probably use just directly it as it is like this. And then, so the next step is then so we can try with the 3 clusters now back. So the K2, that will not give good results. Just a second. So yeah, and if I add 3, then it should give good results, hopefully. But I have radial basis in right now. Okay, the radial basis is not great here. So again, you already see how important it is to understand what kind of the affinity matrix the algorithm has. By default, it has the radial basis, but in some cases, the Euclidean works so much better. So, okay, great. So these 2 lines we just implemented in much more lines. And now let's add even more lines. So I will drop this fixed code in the Jamboard just in a second. And then we implement the last part for today is to have the k-means ourselves here. And probably there are 100 ways how you can implement the k-means. I will do my version. So let's see. So I'm adding this to the slide number 4, this part of the code. Okay, with the gamma 2, we go to the Laplacian matrix. Okay, maybe you're right. I really did that operation of like kind of normalizing the degree matrix. Like I think in most cases there's very little effect for if you get the weighted affinity matrix by the pairwise kernel function. So maybe that's why it worked for you. That in the chat, Christopher is writing that with the Laplacian matrix it also works. So anyways, but here it works also in a very simple way. So, but I think that the coolest thing all about that one is that there is just this eigenvalues and eigenvectors sorted, and that already gives you the clustering properties. That is, and they can cluster those moons. That's really powerful idea, and that's as I understand comes from physics, from the wave equations that it kind of describes the kind of the turbulence in the data or something. So that's really nice hack for the calculations. So here let's do the k-means quickly. So let's see. So we'll have the random centers, center IDXs. So the k-means means that we will start by random vectors that we choose from our existing vectors as the centers for our clusters that we want to find. So here we'll use the NP random. Let's see, choice of NP arrange of the length of this guy, VK. And we want the random choices in the number of size k. So I want like these will be our random centers. So then these will call centroids, and we will select them from VK, from that eigenvectors. So these will be our centroids. By the way, if somebody at some point, even watching this video later, like come across some mathematical formulation why that Laplacian matrix is needed or not needed in those first lines, that would be great. But that we can discuss later as well. So in general, the inputs for the this large function that we used in the very beginning, that you're going to use in deep metric learning and all sorts of cool applications, it doesn't require actually those equations, but it just requires the knowledge of your affinity matrix here. It requires the knowledge of the gamma and knowledge of the this part of clustering, k-means, because again, you can choose what kind of clustering algorithm you want if the k is larger than 2. So that is really important, actually. So, okay, let's see. So we have centroids, then we have the clusters. So the clusters will always be the same count. So let's see. Oh, sorry. Before that one, we need to have, by the way, I need to copy also these dimensions. And then we have the iterations in the range of, let's say, also 1,000. Now we'll have the clusters. For each iteration, we have a hypothesis of clusters for in range of k, of course. So we construct the list because we cannot say how many samples will be in each cluster. Maybe they are not evenly distributed. Maybe one cluster is much bigger than other. We cannot just store them in Numpy array that must be with a predefined size. So then we calculate distances between each of the VKs. So for each of the samples, we have the eigenvector here. So this is really similar to what we did last time with the nonlinear PCA. So VK, centroids, and metric, again really cool. So we can use cosine, we can use Euclidean. It depends on dimensionality. Probably if you have high dimensionality without the PCA whitening before, I would prefer everywhere the cosine distance. The cosine distance will work much better with higher dimensionality. If you have lower dimensionality, that's great with Euclidean as well. Euclidean, because in the high dimensionality, Euclidean distances kind of converge. So they have very similar values. So the clusters, then the Y prims. So I just don't want to have another loop at the end. So I will just have the temporary Y prims always. So that's cool. That's cool. I think that's it for this part. So then we go inside the IDX dist and enumerate the distance. So the C dist would give us, so in this case, let's add what actually happens here. So there is the centroids, that we have 3 centroids. We have 1,000 samples by the same dimension as the centroids. Maybe I should add that information, maybe it's not clear. So if shape is the, so in this case, it will be the 1,000 samples by, so the 3 dimensions, or let's say the, okay, 3 dimensions, and then the centroid shape would be the 3 dimensions by, I mean 3 clusters by 3 dimensions. So 3 clusters, 3 dims. And the output of those distances should be, again, I think it should be 1,000 by 3, where each of those would be what the distance with regards to each of those 3 clusters, basically. So here the 3 is the dimensionality of the vector, and here the 3 is the assignment to the cluster. Hopefully, if my code is correct, maybe it's not correct, but I hope. So IDX cluster, if not correct, we can transpose and everything will be great. So MP arg min of the distance. So this will mean the assignment to the cluster, because each of the samples contains 3 distances to different clusters. And we want to select that one which is most close, that is the closest to the cluster. So then we have the Y prime. So the Y prime is our prediction, and the prediction is important only in the last iteration, but I just don't want to do another loop, so I added here. So, and then the clusters, IDX cluster, append, okay, it doesn't give me autocomplete, append the, so what should we append? We should append actually the VK of the IDX by the sample, so like that. So that's great. And then the last thing for IDX cluster in range of K, in between the iterations, we always calculate the mean value of the centroids. So there will be the, so each of the clusters contains a lot of samples, and we want to use the mean or the average point of that cluster to do the next iteration. In the very beginning, everything is random, and then step by step, everything becomes not random. So here, of course, you can use the mean, then that would be a mean K clustering, but you can also use the median, that would be median clustering. So I think the median works better, but it depends probably on the way how algorithm is implemented. So I think that's about it. So let's see if this works, then I will share that code as well. By the way, the way how I implemented the k-means, that's just one way. There are like literally like 100 ways how you implement this function, this model. So it works great, nice. If I try to do the median, let's see, is it running? Okay, median is so slow. Median is just selecting one vector. Why it's so slow? Okay, it works, great. So the median or mean works, at least because this one is really simple separation. For the not so simple separations, probably would not work so great. So anyway, we'll see with the moons in a second. Maybe it will not be that great, but I really don't know what will happen. We'll see. So I'm adding this part of the code to the Jamboard. Oh, I accidentally dropped to the 6th slide. So I hope that today, at least apart the missing information of should we calculate Laplacian there or the kernel function itself is sufficient. The idea how the spectral clustering works is a little bit clearer to you. And the next time I'm planning to look at the spanning tree type of algorithms. Like in general, for the next time, hopefully I can try to use as an affinity matrix the spanning tree connectivity matrix, but we'll see. If it doesn't work at all, then I will report you as well. So let's see. So here I copied that one to Jamboard as well, but I want to try with the moons, and then we'll end. So the moons, okay, but the moons are 2, so they work. Okay, with 2 moons it works. I don't have 3 moons. Maybe somebody can make like a circle inside the circle inside the circle. Then probably that would be interesting situation. If I increase the standard deviation, let's see what happens. Maybe it will break, but hopefully not. Again, I think this is like crazy cool example of what works great. So cool example of using the eigenvalues and eigenvectors for a completely different task. Like, of course, it's not like really completely different task, because if you think about the PCA, it also is kind of like you can use PCA and then on top of that the some kind of linear regression, and then that would be called support vector machine. And this is just like clustering using very similar mathematics as before. So if you imagine that your embeddings are not like these shapes of these nice clusters, but more something like this, because we cannot really control like everything that could model could predict, then this approach is much more robust than k-means or just like calculating the radiuses or something like that. So I hope that was informative and fun so far. So yeah, I think that's like short tutorial for today. That would be it. The next time I will report results how it works with the these minimal spanning tree as the affinity matrix, and also we'll look at the HDB scan or the DB scan algorithm, I think. So those ones are really powerful for the clustering. I once already in this group shared the one of the paper where we read about the HDB scan, but now I want maybe to implement it as well. So hope it was fun for today. That's it for today. My students, let me know what do you think, and I will also give you some tasks. Okay, bye-bye.